Hello, Ray. Good to see you again.
Hi, Richard. Yeah, becoming a regular thing, isn't it?
It is. I'm enjoying it. I'm enjoying it. This is a very interesting topic to me.
Yeah. Today we want to talk about cymatics. Cymatics itself doesn't show anything to do with harmonic structures. So it's in that way unrelated to harmonics theory, but it did lead me to discover some things that very much did influence the course of what I understood is happening at the atomic level. So I wanted to bring it in to show that.
Okay, can we start with just a basic of what is cymatics?
Yeah, so going back, so Hans Jenny's the man who came up with the word cymatics and did these experiments, followed by Guy Manners afterwards. But long before that, like 100 more years before that, there was a guy named Chladni, spelled Chladni, and he did with violin bows on metal plates and that. And he discovered a lot of the stuff. So that's an interesting background. That plus those two gentlemen are worth looking at their stuff, because if you haven't heard about this stuff, it's absolutely fascinating to see it. So that's a good place to start. Both Hans Jenny and Guy Manners were doctors, and part of their objective in this was to use it for health. And for example, Hans Jenny, what they did is they would put a microphone on a person's muscles, healthy muscles, and record what came out. And if the person had a wrenched muscle, they would put the speaker on the muscle and play back the healthy muscle sound to try and get it to get back into the correct rhythm. And so I can't say whether that's a good thing or not, but it sounds like a good idea to try it at the very least. Yeah.
But the basic idea of cymatics is that vibration or frequency can influence matter.
Yes, absolutely. And we noticed that this is not an originally new idea. Both the Old Testament and the New Testament start off with, in the beginning was the word, or let there be light. Two forms of vibration that we know about. And the idea that that the word leads to form is an old one, but it's still true today. So so that's good.
That
so
sound
it is about,
leads to form.
Yes, yeah.
Good.
Yeah, so that's very important in the whole thing.
Well, shall we start with the slides?
Yeah, for sure.
Okay. All right. So here is just a little graphic of what is this? A book cover?
Yeah. That's from the website, but that's the book, Cymatics by Hans Jenny. And there's a lot of good stuff inside. I'll flash one or two of those up. There's all these, I'm not very good at doing this. There's all these figures inside. And it's been noted by people that some of those things are very similar to the stained glass windows that are in cathedrals and that. So, whether there's a connection there, who can say?
Yeah. Would you like to watch a little bit of the video or go into kind of how it works first?
Yeah, let's watch the video. Yeah.
The film you're about to see has no characters, it has no people. It is a film to describe to you and explain visually the effect of cymatic frequencies on texture, structure, water, oil. If you spare a little of your imagination as you watch this film as it runs, you will see many things that answer many questions. You will see living forms, living amoeba, almost animal-like creatures. You will see continents being formed, the Earth itself coming into existence, explosions, eruptions, atomic explosions and bombs. You can see all this and watch it before your eyes, but everything owes its existence solely and completely to sound. Sound is the factor which holds it together. Sound is the basis of form and shape. In the beginning was the Word, and the Word was God. We are told that this is how the worlds began and how creation took shape. If we put that into the modern idiom and say that into the great voids of space came a sound and matter took shape. Please watch carefully.
We can also use different shapes of plate.
All right, so that was the basic idea, right?
Yes, so that gives you some idea of the sort of things that can happen.
And you're going to kind of explain to us how this works now?
Yeah, well, when I saw this stuff, when I saw Jenny's books and some of the videos are available, I decided I've got to have a try at this. And so, well, no, actually another thing happened first. That was quite entertaining. I had a cup of tea, and I noticed that when I put it down on a hard surface, some rings came in from from the edge of the thing into the middle, and they concentrated, so the wave got bigger as they went inwards. And so I sat there jiggling it like this to try and get them going really well. And when I got the frequency just right, a jet of tea shot out and got me in the eye. And at that point, I thought, okay, there's got to be a better way of doing this. So I made a little apparatus to try and do this. So so let's look at the apparatus.
All right, so I'll pull up those slides here.
Yeah, this one. So I had a little dish mounted on a speaker, and I had a video camera, and I had a light so that the light would reflect directly into the camera. So and there was water in this dish. So if there's no vibration going on, then the water all looks light. You're getting a total reflection of the light. But when you get vibrations, the places where the water's flat will reflect the light into the camera, but the places where the water's tilted in any direction will send the light somewhere else, and you'll get dark patches appearing there. And so it shows quite clearly what's going on. Yeah.
Interesting.
So that's just showing the detail of the speaker. So the lower part there is the speaker, and then I had a little plastic thing and another little plastic thing. I tried it with he had different times, he had powders. I tried it with some sand, but all that did was fall over the side, all over my speaker. So I got rid of that and put water in the dish. Water seemed to work quite well.
So you were able to just use water instead of sand, but you reflected the light off of it so that the camera would only pick up the flat parts of the water. That's ingenious, Ray. Well done. All right.
And then when I did it at a low volume, I got something like this, like the rings I mentioned in the cup of tea.
Okay.
Then as I increased the volume of the sound that was playing in there, it suddenly went to this pattern. But it was sitting there stable, 6 circles around a circle. We know that pattern. We can do that with pennies or something. It does that, and some little ladders running out. Then when I increased the volume still further, these things broke loose, and they were all moving about then. And we can see this as like 3 states of matter, sort of solid, liquid, gas or something happening there. And these little ladders running out to the side. So these are my crude drawings of what happened, but you can't get it in between those things. They're discrete changes that happen as you increase the volume or decrease the volume. It suddenly goes from one of those to the next. Now, this next one is an actual shot from the video, screen capture from the video. And you can see this was the 3rd state where it's getting very active. And you can see these little circles of stuff going there. And you can see the little ladders running out.
Center one, and then the kind of 6 around the edges.
Yeah, that's not got the 6 around. It's got a sort of different arrangement. And I look into the geometry of that next. Okay. So, so I've labeled them with blue and with red. And the reason for that is the number of half wavelengths is very important. If the points A, C, X, Y, Z, I'm saying Z, we say Z, are all up at one point in time, then B and D will be down. And when the red ones are down, the blue ones will be up. How do we know this? Because we can count from A to D, we can count 1, 2, 3 half wavelengths. And the same from A to D, B, from B to C and C to D, they're all 3 half wavelengths apart. So that means that A and C are going up when B and D are going down, and then they're going down when the others are going up. And the X, Y, Z are doing the same as C because they're all whole wavelength, 2 half wavelengths apart, and all of them are 3 half wavelengths from D. So you can't see that even in the video. You have to understand what's happening with the light reflecting to work that out.
Interesting.
What's interesting about it is there's definite bond lengths there that these things are sitting apart. The whole thing is quite fluid and moving about, but the distances are maintained in many cases. So I began to see this as being like charge particles. We have plus and minus charge. So like, the red ones might be plus and the blue ones might be minus. They're opposite phase in the oscillations. Mm-hmm. And in fact, when you get further into, in case I forget this later, when you get into the quantum mechanics, the quarks, they have 3 states. They call them colors instead of calling them plus and minus. They have red, green, blue, and they have 3 states. And I think it's possible that instead of having just two phases, you've actually got 3 in that case. It'll be a more complicated thing again. Bear in mind, what we're doing here is only in 2 dimensions. So I'm trying to think about it in 3 dimensions as well. What has the world got happening in these particles and so on? And I think that this sort of thing gives a picture of what goes on in those areas, which if physicists were to take this up and trying to make physics models, they wouldn't need 11 dimensions and all this sort of stuff, 10 dimensions, whatever they're up to. You can do it in 3 dimensions if you've got the correct equations and to understand what these waves are actually looking like. Yeah. So that's just showing you the distances between them. But now there's some other interesting things happening as well. If we do a series of lines here, and you can see the beginnings of a ladder at the lower left running outwards in that direction, and there'll be one up to the right as well. If we put regular red, blue lines at half wavelength intervals, you'll notice that the blue ones always hit on the blue things, the red ones hit on the red ones, right? So they're all, so a wave that runs through in that direction is in phase with all of those. So is the one that runs up to the right. Yep.
Okay.
Yeah.
Go to the next one.
Yeah. Let's see what the next one does. And also, every one of them, if we do the half wavelengths going out from each one, all the other ones of the same color happen after an even number of wavelengths, and all the ones of a different color happen after an odd number of half wavelengths. So every one of those is supporting every other one in its existence. The waves coming out from one are going into the others and supporting them. So that's why it's a stable pattern. It keeps going over time. Yeah.
Interesting.
Yeah. Now, in my case, I had the edge of the thing, and they were bouncing off the edge and coming back. Those ones there were 3 half wavelengths apart. I've drawn those 4 centers there, and you can see I've tried to show the circles going out and the directions of the ladders running, and you can see there's ladders running, up at 2 o'clock sort of thing, and 8 o'clock, and at 11 o'clock, and at 5 o'clock. But that picture is, if you reflect it horizontally, you'll get another 4 directions as well. So you actually get 8 directions of ladders coming out from this thing and bouncing off. So what I see is that atoms and particles are sitting there with these arrangements, and the waves coming out from some are the incoming waves from the other. We'll come to that in more detail when we look at the atomic structures. But it continues to support itself over an extended period. Now, because I'm doing it in sound in the dish, and sound is getting lost, you have to keep doing the sound to keep it going. But in fact, in the universe, there's nowhere else for the waves to go. So they will continue to exist indefinitely unless something very dramatic happens and will turn it into some other type of particles instead. But that's the sort of thing I see is going on in atomic particles.
Okay, and how does this relate to harmonics?
It doesn't yet. Well, other than that, there's waves of particular periods, particular wavelengths, and the idea that this is charge. So we'll come to that later when we look at the actual atomic particles and how they relate to each other.
Okay.
But it's an interesting study in its own right, and it's all very much cycles things. So that's in the lower right one, I've showed you those four already, but the lower right one is showing you that in this case, there's actually 12 ladders running out from it from that one in all directions.
Calling them ladders or letters?
Ladder. Yeah, ladders. So what I mean by that is these little lines. So in the top left diagram, you can see one running almost vertically downward, just slightly to the right.
This one?
You can see, and there's one running, a strong one running up to the left, right to the top left corner. So I call those ladders. They've got like rungs, right?
Okay,
yeah. You can see a bunch of them running off in different directions.
Okay, yep.
So what's happening with that one? It's hitting the edge of the dish and coming back again and rejoining the pattern in phase with all of that stuff.
Mm-hmm. Yeah. Got it. Okay.
Yeah. So that was a cymatics. Now what we're looking at is there's a few people have contributed to this idea. When I realized that the harmonics pattern went down and came to the correct place for atoms and subatomic particles, I realized they had to be standing waves of electromagnetism. And I put something on the internet about that. And I got an email from a fellow named Milo Wolf. And he said, welcome to the club. And I said, what club's that? He said, the club that understands that particles are these standing waves. And I said, oh, good. How many's in the club now? He said, 2.
And who is Milo Wolf?
Milo Wolf. So he's an American physicist.
Okay.
And we'll come back to him in a moment. But within a couple of years of that, there were about 10 people in the club. But in actual fact, there had been people in the club before. So what Milo did is he showed a model, which we'll come to in a moment, for electron. And he proved that all the properties of the electron were consistent with this model of a standing wave of the electron. Now, he wasn't the only person looking at this. A couple of famous American physicists, Wheeler and, was it Feynman? No, Wheeler and somebody. Was it Feynman? Anyway, they did this model. And what you've got to, it's tricky to imagine this. The other thing may show it, but if you get a sphere and you run a line out from it in each of the 6 cardinal directions and up and down, you know, then and then what you do is you rotate the sphere through 180 degrees, and then you give it a spin. You think that those 6 lines running out from it are going to get all tangled up, but they don't. And this shows as you go through these diagrams here, it shows how it goes from the beginning back to the same place again. And you'll notice that halfway through, it's the mirror image of what it was at the beginning, and then eventually it returns to the same state.
Now, so here's where it begins. This is the halfway point where it's the mirror image, and then it returns to the same state here.
Yes, yeah, and it's a bit hard to figure. The best way to do this is to get 6 bits of elastic or rubber band, something, running them out and put a ball there to a 180-degree turn, and then start rotating it and see what happens. And you go, oh, it doesn't get tangled. So in my view, what this is it's the ether has got this part, which has got this rotation, and it's spinning. And the things go, I can't do this with my hands properly. They go under one way, and then they go over the next time. So it sort of starts to tangle it and then untangles it, and so on. And we'll see some diagrams of that in action. But the guys, Wheeler was it Feynman? Wheeler and Feynman. I may have this wrong. It may have been Wheeler and somebody else. Anyway, they actually mentioned this in one of the main physics textbooks that's used in America, or has been used for a long time, as being the explanation for spin half, that this thing has the spin half. You've got to go around twice to get back to the same position. And it's known that a lot of particles do have this spin half property, which is, it's pretty weird to understand until you see this. So it's a reasonable model, but Milo went so far as to prove that this explains all the properties of an electron. Now, these guys had this idea of waves coming out from an electron, and then they said there's waves going outwards forwards in time, and there's waves going outwards backwards in time. Now, to my way of thinking, waves going outwards backwards in time is waves coming inwards forwards in time. It's a much more sensible way for us to think about it.
Right.
So there's waves coming in, passing through the center and coming out again. It's the same wave after it goes through the middle. And they got so close, those guys, to getting this correct, but they didn't take the final step, because the final step is to say that's not what happens to an electron. That's what an electron is. It's the entire explanation of the electron if you get rid of this backwards in time stuff. So so let's have a look at those. I think we got these other ones next, the video one. So this was what I called the wobbly project. Now, this is trying to do that sphere rotating in space. But what I've done is, you can't see the whole thing. It's too complicated. What I've done here is a slice through it and showing what happens with the slice. And you can see that there's something going around clockwise there. It's going up in one place and down in another. There's actually a whole 3D structure around that. So it's very hard to follow the whole thing. But you can get the idea that there's some circular motion going on. You can see the waves sort of going outwards from it as well, and inwards, but it's a bit hard to see those, but there's waves going in and out. The other one, next one, instead of doing a slice through it, I did 3 slices so that we got a corner in the next one. So you can see the corner in the middle there, and you can see the 3 things there at right angles to each other. I've got a version of that somewhere that's done with red and blue, and if you put 3D glasses on, you can see it properly in 3D.
Oh, interesting.
Yeah, but that gives you the general idea of what's going on there. So this is all consistent with Milo's description, but he wasn't actually the first one to look at this.
So this is essentially slices of these rotating.
Yeah, what I've done there is, when that thing starts, he doesn't show the starting position, but if you've got a ball and you run one string upwards, one downwards, one left, one right, one outwards and one forwards, that's the starting position. And then you rotate the ball by 180 degrees, and then you give it a spin, and that's what you get. And you think those strings are going to get tangled, but they don't. And you can, it's not that there are strings there, but if we're thinking in terms of the ether, there's substance everywhere. Let's imagine we had some what we call jelly and you call jello, and somehow the hand of God reaches inside and rotates some 180 degrees and then gives it a spin. You think, okay, that's going to just rip the jelly apart, but it doesn't. It gets a little bit tangled and a little bit untangled, and it keeps on doing that, like those slices we're showing you.
Okay.
So it's hard to picture. So this is why it took a long time for people to get to this sort of idea.
Okay.
Now, this diagram is showing you, you know how all the chemical elements have, like you've got hydrogen has got mass 1, helium's got mass 4, carbon's 12, oxygen is 16, and all this sort of stuff. And they cottoned on to the fact that they were made of some number of smaller things, which were protons and neutrons, and they could work out the mass of those. Now, they weren't exactly 1 and 4 and all the other numbers. They were slight deviations from it, and they call that binding energy. They don't. It doesn't. Not really an explanation. It's just an excuse. But I decided to try the same thing with the mass of subatomic particles. And what I put into it originally was a bunch of subatomic particles that are known. There's more and more been discovered since then. I did this quite a few years ago, so that I presented. If we go to the next diagram briefly, that's the actual one I presented at the Foundation for Study of Cycles. There we go, 1994. And so at that time, I predicted there would be this other new particle, 17 times the mass of an electron and 1/27th of a proton. So that was the structure I had then. Let's go back to the other one because it's slightly tidier. And so X is the new one I was predicting. Now you can see there, I've marked the ratios between the masses of different things. Now, why mass? Because in cycles, it's frequency. Two of the things that came out of quantum mechanics were that Einstein said E equals mc squared. So he's saying energy and mass are strictly proportional. Planck said E equals h frequency. So he had his constant. So he's saying energy and frequency are directly proportional. Now, so that's saying there's three things. Frequency, energy, and mass are all really manifestations of the same thing. Now, one of the Americans who got a Nobel Prize in physics, I thought it might have been Steven Weinberg, because this guy was in Texas, I think, but I can't find the quote where he said that. But one of them said there are these three things, and he said, probably if we want to say what's the most fundamental, it's probably frequency. So basically he's agreeing with what I'm saying here. It's not necessarily how everyone thinks, but everyone knows that energy and frequency and mass are all in proportional under these circumstances. So we're using mass here, but it's being it's standing in for frequency, right? So these are frequency ratios. So we've got these ratios of frequencies or periods, exactly the same as you had with all these other things we've studied. It's just that now we're down in the frequency range of around about 1 million cycles per second. Pretty fast, those gliders. And so remember that we had got a 5 and a 7, and we got an 11 and a 13 up further. Down here, we've got a 17 and a 19 and a 23. The higher primes happening in the correct order that we think they should, but they may not be the first occurrence of those. Yeah.
And the 23 down here.
Yeah. Now, how did I get this thing? Well, let's look at it first. So you can see 2, 2, 17. Then we go down 2, 2, 2, 2, 2 that way and a 3 there, and 3, 3, 3 the other way and a 2. And then after we come down by the 19, we get another bunch, 2, 2, 2, 3, 2, 2, 2, 5, and a 23. There's another whole set that are related by 2s and 3s, but I'm not quite sure how that links into the other part. It's it doesn't. There are a couple of possibilities, and I don't know which one's correct. So that's the basic picture of
these are particles.
Yes, they're all particles. Now, very
quantum particles.
Hey?
Quantum particles. Subatomic particles.
The electron is stable. And on the left-hand side up the top, Pn, proton and neutron have got essentially the same mass, and they're stable. Well, the neutron's only stable with a proton. If you take it out free, it only lasts about a quarter of an hour, and then it goes boom, somewhere in that. It's got a half-life of that. All the other ones are unstable, and they will all fly apart and make other things. So, but for the brief time that they exist, they can get their tracks in the cloud chamber. They can work out their mass, and their energy and so on, and their charge and lots of other stuff. These ones at the bottom, Z or Z for you and W, were some of the more recent ones when I did this down there. Since then, they've added the, what's that one they were looking for a long time? Higgs, the Higgs boson. I haven't got the Higgs in there. I don't know if they know it accurately enough to do this. Maybe it throws another prime in, I don't know. Maybe it's 29 times that or something. But anyway, that's the one. Now let's go forward one more from there. This is the results I got. So those are the particles I put in on the left. Then we've got their actual mass. And then missing the next column, we've got the multiple of the 34.76 million electron volts that I predicted should exist. And the electron's 168, all the others are multiples. And we can do the factorization there showing the 2s and 3s and 17s and 19s. Then if we assume that that factorization is correct, the middle column has got what would be the mass of that particle. And you'll see that in most cases they agree quite well.
So just going back to, this was the particle that you predicted that hadn't been discovered. It's
That's
the
correct.
X particle here.
Yep.
And
this is all
why
done in
did you
terms
predict it to be 34.76?
because it's 68 times an electron and 1/27th of a proton.
2 times 2 times 17?
Yeah. Yeah, that's right. That's
okay.
So 68 times that. Yep.
Right.
And 1/27th of a proton. Notice that
3 times 3 times 3, so 1/27th of a proton. Okay.
Yeah. And notice that 68 times 27 gives you 1836, which is the electron to proton mass ratio.
Okay.
So yeah, so in here, you can see that in most cases they agree moderately well with those other ones. Now that prediction I made it first.
When you say most cases they agree, I'm not sure exactly what you're talking about.
Well, we're looking at the actual mass, like 105.6 for the muon, and this one says it should be 104.3. So it's a little bit out, but not much. It's the same sort of difference as you get with the elements,
and
not being
it should
1,
be
104.3
because that's 3 times 34.76.
That's correct. Yeah.
Okay. So these are the multiples of 34.76. So the muon 3, if we go back here, the muon is 3 times 34.76.
Yeah, and the proton and neutron are 27 times. So you can go back and look at those. Yeah.
Got it. So the proton is 27 times down here, and the neutron. Okay.
Yeah.
And so that would give a theoretical mass of 938.5, and we get 938.3. That's pretty good.
For the proton and 939.6 for the neutron. That's slightly different. There's obviously something a little bit different with the neutron. Some people think it's just a proton with an electron that means splattered onto it, and that's probably a reasonable explanation. So
did they discover this particle?
Yes. Well, now I originally predicted this before the Foundation for Study of Cycles conference. I predicted it on Usenet, and I further predicted it again at the Cycles conference. Now, I believe there were sound recordings made there. There were no video recordings, and I don't know if the sound recordings exist, but that's my original one that I presented there. And most of them just ignored that because they didn't have anything. And one of the guys said, well, you're right, he said, I'll look into it. So he then tried to reproduce this thing I've got here. He put the particle masses in, and I told him how to do Kotov's method to find the things, which he did. And he got the results. And you actually get two values out. You get 34.76 and double that. But I didn't like to double that because there were 27 of these things in a proton, and there would have only been 13.5 if you picked the double one. So I used the other one. So he got to that, and then he wouldn't admit that I'd done that. He admitted I could have done that, even though there was evidence in the Usenet thread. He admitted I could have predicted, but he said that's not a particle. And I said, why is it not a particle? He said it's not in the physics particle handbook. I said, why isn't it in there? He said because they haven't verified it. Now, they had done an experiment that found it, and other people had tried to repeat this, but the results weren't entirely consistent. And I said, as soon as they find one new particle that your standard model predicts, you put it in the handbook, don't you? Yes. And if they had predicted this one, you would have put in the handbook, wouldn't you? Well, I suppose we would have. And I said, but because it's an alternative theory, you don't. So you can say the alternative theory wrong. Why is it wrong? Because it's not our theory. And in the end, I got him to admit that. And he said, yes, he said, I will agree that what you're doing is science and you're doing it properly. It's just in a very different field to what I'm doing, and I'm going to stick with what I'm doing. And I said, oh, more loss for you. So that was some funny little stories there. Sorry about the rude bits.
Got it. All right.
It's not a complete story without the rude bits. So we also find, I don't know, I don't think I've put the diagram in there. I might have, I don't know. If you analyze things not by elements, but by the mass of the nucleus, because there's often isotopes for different ones, right? If you analyze them by the masses of the nucleus, that's not this diagram, it's another one. It shows how common each one is. And you will find that, for example, 14, 28, and 56 are very common masses for the heavier elements, and 1, 2, and 4, and 12 are common ones for lower ones. Now, in the sun, the process that happens is hydrogen combines to make deuterium, it combines to make helium, and no one knew how you made the heavier elements. In the supposed Big Bang, you could make up to helium or slightly further, but you couldn't get to carbon and all the bigger ones. And so that was the problem. Fred Hoyle, who was a very bright chap and who I admire very much, he solved this carbon-12 one, but it took him years to convince them to look for, in a particle accelerator, a special state of carbon-12 that would prove he was right. And eventually they did it, and they did prove he was right. But in harmonics theory, if you remember, the strong harmonics go 1, 2, 4, 12. So harmonics theory could have predicted that you would have to go to carbon next. And that's the pattern of it. What we find is in the sun, we don't have the carbon, but we have the hydrogen, deuterium, and helium. Only when the helium has, when most of the hydrogen is being converted to helium, the sun will then stop burning hydrogen, and it will start to compact under its own gravity. And at that stage, it will start to burn helium to make carbon, and that becomes a much brighter star then. So we find in the sun, and also in Jupiter, Saturn, Uranus, and Neptune, we find these atomic masses 1, 2, 4. That's what they're made of. And that's what you get as you go towards the middle of the sun. You go from 1 on the surface to 4 in the middle. If you look at the Earth, it's quite different. It's not got lots of hydrogen and helium. It's got some, but the most common element in the atmosphere is nitrogen, it's got an atomic mass of 14. The most common elements in the crust are silicon and oxygen. And silicon's got a mass of 28, oxygen 16. And the most common element, just about the bulk of the core, is iron, atomic mass 56. So we see there, we're doubling again, 14, 28, 56 is happening as we go.
This time you're kind of going outside to inside versus inside to outside.
No, it's the same order. The outside, the lower numbers on the outside and the highest on the inside. So as you go inwards, it's combining now. So this is another one that people say, well, that's a good coincidence. And I say again, yes, I've got some more. And so that one, I don't know what this means. It can mean two possible things. No, I need to give you more of the coincidence first. If you take the orbits of the outer planets, those were those 160 and 80-minute light distances from the sun. And the inner planets, which the Earth is one of, at 0.35 and 0.7 astronomical units, at 3 and 6 light minutes, it turns out that the inner planets are on an orbits that are 7 or 14 times smaller than the outer planets. So the frequencies of them are that many times higher of the standing waves that cause those to be developed in those places. So what we're finding is, if we actually look at those big steps that we get in the harmonics theory of typical ratio 3, 4, 5, 6, 0, remember there were these big steps. We went Hubble scale, galaxies, stars, planets, moons, etc., and we get on down finally to atoms and subatomic particles. Those big steps, the difference between those elements, frequencies, and the spacing of those orbits is 6 of those big steps apart, very accurately 6. So it means that there's two possibilities. One is that the orbit that they're in is the frequency of waves it's getting of the cosmic waves that are coming through all the time. And that as a result of that, it works all the way down through 6 levels to make these elements. And they could be getting made in the Earth. Now, that's a radical idea, that these elements from the nitrogen might be making silicon and iron in the Earth over long periods of time. Or the frequencies there attract those elements to those places. That's another possibility. I can't say which of those is true, but for sure they're there. So that's that's very much in fitting with the whole harmonics theory that that structure exists over many levels of those large-scale structures.
Mm-hmm. Okay.
I can't remember what we've got after this.
That's the end, other than the Schrodinger quote.
Oh, okay. Righty-ho. Oh, let's do Schrodinger again. Yeah. So he's saying all these bodies and forces are nothing but shapes and variations in the structure of space. Particles are just, I don't know how to pronounce that, Schoenkommen appearances. So I believe that's correct. He's not the only one. I found shall I read you another one from Tesla? Did I send you the Tesla one?
You did. Yep. I can probably find it if you'd like me to pull it up.
I can probably get it.
Okay.
Sent. Shall I read this one out?
Yes.
On his 75th birthday, Nikola Tesla gave an interview with the press. During the interview, the conversation led to the subject of the human mind. This is what Tesla had to say. We are all automatons. So he's gone further than just saying these things influence us. He's saying that's entirely it. In fact, Chizevsky almost said that. I think Dewey held back a little bit from that. I think he didn't want to do something that was too unpalatable. We're all automatons, he reflected, obeying external influences. We are entirely under the control of agents that beat on our senses from all directions of the outside world, being merely receivers from the outside. It is a very important question how good the receivers are. Some are sensitive and receive accurately, others are sluggish and their reception is blurred. The individual who is a better machine has so much greater chance of achieving success and happiness. An individual who is an offender of the law is a machine in which one or another organ has been deranged so that responses are no longer accurate. There is no chance in nature. So he's saying there's no chance. Einstein said that too. I'm with these guys, Tesla and Einstein, there's no chance. Most of the people who do quantum mechanics think there's chance. Although the modern theory of indeterminacy attempts to show scientifically that events are governed by chance, I positively deny that. The causes and effects, however complex, are intimately linked, and the results of all inferences must be inevitably fixed as by a mathematical formula. I also absolutely deny the existence of individuality. It took me no less than 20 years to develop a faculty to trace every thought or act of mine to an external influence. We are just waves in time and space, changing continuously, and the illusion of individuality is produced through the concatenation of the rapidly succeeding phases of existence. What we define as likeness is merely the result of symmetrical arrangement of molecules which compose our body. He says there is no soul. What about the soul, the spirit, he was asked. He replied, but there is no soul or spirit. These are merely expressions of the functions of the body. These life functions cease with death, and so do soul and spirit. What humanity needs is ideals. Idealism is the force that will free us from the material fetters. So that one was done in 1931. Oh, hang on. Those quotes are from 1931. So that's mixing up some stuff from 1930s and 1970. Interestingly, a lot of that stuff a lot of the stuff he's saying there, that he could trace these actions on his body and so on from these things, sounds very similar to something else I do. And I've mentioned to you, I won't be able to do one of these in 2 weeks' time because I'm going to be away on a 10-day Vipassana course, Vipassana meditation. And that is the teaching of the Buddha. The Buddha also said there's no self. We have this illusion of a self. We have this illusion of free will. We have this illusion of doing things, but it's all this stuff coming in from outside that if we learn to see it, we can be a bit more free from the domination of that. But it's yeah. So
I think it's one of the ideas that makes cycles, you know, controversial and a bit unpalatable to all of the institutions and people that are invested in believing that we're in control, right?
Yeah, yeah, absolutely.
Although, you know, personally, I don't fall on the pure mechanical thing, because to me, there's always the question of, okay, even if you want to talk about all the external forces operating on a receiver, what's the receiver? Right? So I think these are, you know, we can have an honest debate and honest opinions on either side of the debate, but there's definitely more than meets the eye.
Yeah, that's right.
And clearly there are forces that are influencing us, that are leading to thoughts and feelings, etc., that you know, that we don't have to claim those thoughts and feelings as the self, right?
No.
And yet I've never been satisfied with the notion that there is no self, because it just doesn't make sense to me, you know, because there's always an observer and an observed. There's always a subject and an object. There's always a knower and the known. And they seem inseparable to me.
Well, there's always a knowing. There's always a knowing and an observation, but there isn't necessarily an observer. There's not necessarily a subject and an object. There's just something that happens.
Yeah.
And our language makes it like that, but it doesn't have to do that.
Sure does.
But I agree with you. You don't have to go to that extreme. I think Tesla's at one extreme there. I think Einstein. I think Chyzewski was somewhere in the middle. Do we move some way down that, but not the whole way?
I think he was reluctant to share his complete views, is my guess. But
yeah, it's quite possible. I think that, as you say, people don't want to accept that. So I'm an old guy. I'm past caring what they're going to think about me. So I can say these things. It's other people got to live in the world, make a living. They may not want to say those things. So that's okay, but they should be aware that there is that possibility.
Yes, absolutely. So just kind of wrapping up for today.
Yeah.
Remind me one more time. So we started talking about cymatics, and then we ended up back in harmonics theory at a subatomic particle level.
Yeah.
What was the connection between cymatics and the subatomic particles?
Well, when I did my cymatics experiments, I got these waves at its half wavelength multiples apart.
Right.
And you could see the ladders running out from them. Now, in the real world, it's three-dimensional, not two-dimensional, and there's no little circular dish there. It's the whole universe. Right. So you've got to make the translation from that to the other. But I do see evidence in a number of experiments people have done. They've actually had evidence, although they didn't realize it, that show that some matter here and some matter over there, the waves are passing between them, and there has to be a whole number of wavelengths between them. And so, for example, if you have an electron jump in orbital in an atom here, and a photon is supposed to be emitted and travels to there, and then it does the reverse action over there, those things can be seen as that sort of process. And in my view, the distance between those, if they get coordinated, has to be some number of wavelengths. And so if you've got, say, a crystal with atoms in a structure, and there's waves passing between the different atoms, there will be these whole number of wavelengths. So the cymatics is a means to see the sort of things that are going on, because it's very hard to describe exactly what's happening in there. Mathematically, it can be done, but it's not easy to conceptualize. I recommend people to do this thing. Get a ball, that's a string going out, rotate it 180 degrees, and then start slowly rotating it and see what happens to the strings. First of all, you think this is going to make a fine mess. Oops, that's all come undone again. So that's what's going on, and that's what Milo Wolf's proved an electron is. No one's done a proof for protons and neutrons, because in the electron, it's much more simple. The proton and neutron have got internal structure. they're called quarks or quarks, and so we can't say exactly how it is. In my opinion, there's probably a threefold thing rotating, around each other, and maybe it's 3 of one phase and 3 of the opposite phase, or 3 different phases and their opposites that make up those color things in the rules for the structure of those.
I wonder if we could find a YouTube video that shows the ball with the strings.
Yeah, I think there is. I think I've got one somewhere. I should have dug it out, shouldn't I? I've got too much stuff. Whenever I find things, I start putting in this one place where I've numbered them all. At some point, I'll find some more and put them there. At some point, I'll put that whole lot up as a list of all of the diagrams. I may make a web page with all the diagrams and a very brief description about what each one shows. Not trying to repeat all of this, but just showing that these are the things that are useful. The other one I want to do at some point is I've got a list of people here who have influenced me in my journey of cycles and harmonics, and it's quite a big list. You're on there, Richard.
Wow.
and
I'm honored.
Cycle. So these, there's great scientists there that are well known. There's other people that have been in the Cycles Foundation. There's other people who have done astronomy or physics. There's the famous cycles discoverers like Schumpeter, Hirsch, Gann, Elliott, and so on. There's Hans Jenny and that. And there's different other ones all the way down. I haven't mentioned Yuri Ivanov. We should have had his ones as well. I recommend people to look up the web pages for Yuri Ivanov. Milo Wolf mentions him as well. Now, he actually came before Milo, so he should have been in the club too. And he has these diagrams that show the wave patterns coming out from different particles and making the where they meet each other, and support and cancel each other. And there's all these other ones. We should also do Gabriel Lafreniere. He's I should have had these ones on this one. He was both Milo Wolf and Gabriel are now dead. Gabriel made some very good animated GIFs of what particles do and how things happen. And I don't agree with him on everything, but his animated GIFs are absolutely wonderful for making a lot of stuff clear. So for example,
to find some of them for next time.
Now if you look on the Cycles Research Institute site, there's a page about him. Gabriel, there's go to the wave structure of matter in the index, and you will find both mention of him and Ivanov, and you'll find some links there to good material. Oh yeah, that's right. You can do that right here now, can't you?
You can do it right here, right now. So,
now somewhere up in those index, wave structure of matter, bottom one of that one.
oops.
Yeah, so that little diagram at the top is one of Ivanov's ones.
So you have
he calls them spiders, and down the bottom there's a bunch of links here. So that's the things he come out, these sort of interference patterns, and when particles move relative to each other or accelerate, these are the patterns that are made. He calls them spiders. Yeah, so they are worth looking at. His site has gone, but it's been reproduced by somebody else on KeelyNet. He's an interesting man on KeelyNet too. Hang on, I better put him down on my list of people.
He's on the Wayback Machine. Okay.
The guy that does KeelyNet collects a lot of interesting physics stuff and puts it all there on his one. Yeah.
Okay. Right.
Now go back to that wave structure of matter page again. Oops, no, too far back.
You want to go?
There's a couple more links in there.
Here, let's Close this. Okay.
Go back one
So
from
if I
there.
go back. Gabrielle
Yeah. So those links down there. So, yeah. So now, if you scroll up a little bit, you'll see. So the top three are showing in 2D what the incoming wave and the outgoing wave for an electron. So the incoming and the outgoing, that the other guys didn't quite get right, the main physicists, and what it makes. Then what happens if the particle is moving, how it comes in, how it goes out. And then you see not only does it make this thing oscillating in place, but there's these bands moving across it. Now, those things are known. Wow. De Broglie predicted these things. He didn't predict it looks like that, but he predicted that there's the phase velocity. There's three velocities associated with the particle. And they are these bands. It's not the particle itself that's moving. And these bands can move faster than the speed of light, but they're not really. They're only an optical illusion.
It looks like a rose.
Yeah.
That's interesting.
So Gabriel had a lot more stuff than that. That's just a little taste I've done there.
Yeah.
Go back one step again. So we've got space and motion. Jeff Hazelhurst, he did interviews of Milo Wolf and a lot of other stuff. He's got some of my stuff and a lot of my stuff and a lot of other stuff. And he's built this massive website. And I think, I'm not sure if he called it as the one that coined the term wave structural matter, but before you go, okay, we've gone. He's got huge amount of stuff. So these are some sites for people to explore.
Okay, great.
If they want to know more about these things.
Thank you. Very good.
Who else? We've got Rhythmodynamics is Yuri.
Ivanov.
Yeah.
Why is this crossed out? Is it not? Doesn't work
because
anymore?
that site's gone. But his one, I think, we found it on Yuri Ivanov's cycle, or you can find it on the way back, as you say.
So the Yuri Ivanov is on the way back machine, and then you mentioned KeelyNet.
KeelyNet, yeah. Now, what's his name? Jerry something. I've got to add him to my list of people that had an influence. I can't find it. I've got too much stuff.
Good. All right, Ray. Well, I think we've covered some good ground today. And I hope you have a great retreat and look forward to continuing in a couple of weeks. Yeah. Do we want a tempter for the next one? A what?
Something to tempt them to come back.
Sure. Why don't you share a little bit about what you want to do next time?
We've found that there are these patterns in space and in time, and we found that they match up. So the waves at the speed of light, but there are other speeds of waves other than the speed of light, and there's the speed of sound, and there's other things. I'm going to explain then why there are these other speeds. So, for example, when you have an atom, it's sort of big, but there's a tiny little nucleus there. Most of the mass is in the nucleus. When you have an atom bump into another atom, the sponginess is the atom, but or people call electron shells, but the mass is in the nucleus. So it goes much more slowly. It bounces off each other. So instead of getting the speed of light, you get a speed of sound happening in those waves. So when you back something solid and a wave goes through it, it's at that much slower speed because the atoms are bumping each other, not the nucleus. And it turns out there's not just one level of that. There's about 5 different levels of these things, and they match up with the elements of the ancients, and it leads to a structure which is 2-dimensional instead of 1-dimensional in terms of just time or distance. It makes a thing where we can see linkages when they have the common period or the common wavelength. So that thing becomes quite fascinating, and it leads us into some studies which do start to link up into the spiritual area. So it's appropriate that I'm going on with the Vipassana course now. When I come back, we should talk about that.
Sounds good. Very good. All right, Ray. Thank you so much.
Very good, Richard.
Have a good day.
You too.